Greetings everyone, welcome back to Calc 1, starting the next unit on applications using integrals besides any of the motions and the physics and things like that. These are geometric applications having to do with a lot of the objects that we study graphically. This is the last unit of Calc 1. We're getting excited here, so let's get started. Area between curves. This is not much of a jump from the integrals and the way that you've already been shown them. So far, what you've seen is that a definite integral can represent the area between the x-axis and a function's curve. It also can represent some other weird net signed area sum if you have a combination of different areas. And if you want to do an area, you have to be aware of where you have to section it. Okay? So area between curves has the same kind of ideas. I have some that I can just do one quick integral, and I'll have some where I may have to break them up into sections, right? Anytime you're going to be adding up all of one type of number, all positive or all negative, then the definite integral is going to represent the size of the area, as long as you know whether you're integrating purely positive or purely negative in an entire group, right? And whenever you have a single function, all we look out for are the x-intercepts, and then we split it up. If I integrate from a to c here, I'll get all of these positive numbers. If I integrate from d to b, I'll get all of these positive numbers. And if I want this to represent area, what we've said before is I'm going to take the absolute value. And you know what that means is I'll be dropping off the negative. I want to put a little twist on that by saying, you know, another thing you could do instead is if you knew already that that was a negative region, right? Maybe the graph is something you're familiar with. Then instead, what you're really doing is you're just integrating the opposite of the function. Because if it's already negative, the opposite, the negative, will then be positive, and you'll get nothing but the pure positive area there, right? So it's a different way of thinking of it, but just as good if you happen to already know that that section is negative. Okay, so we use definite integrals as one way of finding area between an axis and a curve. So area between two different curves. If I have a function f and a function g, okay? If f is greater than g on an entire interval, in other words, if the y value of f is more than the y value of g on an entire interval, then the area between them is simply the integral over that interval where I do the f function minus the g function. Let's think about why that makes sense for a minute, okay? Think about it in terms of what's going on right here at this line right here. What I want is the length that's between the two functions, right? I want the length that's between them. So then what I will be doing is integrating f, which is everything between f and the axis, and I'll be integrating g, which is everything between the axis and g. And if I subtract off the piece that's under g, then I'll get the piece that's in between them. And that's all we're doing. Vice versa. What if I were integrating where g is beneath right here? It's the same idea. If I do f is going to be the distance from here to here, from the axis to the function, and g is going to be the distance from the curve up to the axis, and it'll be negative, but I'll be doing minus a negative. So I'll literally be just adding these two lengths, and I get a positive anyway. So it doesn't matter that g went negative here. What matters is that f was greater than g the whole time. So even if g is negative, the subtraction of f minus g will always be positive if f's y value is greater than g's y value. Okay? So the area between the two curves, if f is greater than g on an interval, you integrate on the whole interval from a to b, and you do f minus g, top minus bottom. Sounds familiar, right? It's a common theme here. Now, what if they switch? If you have a situation where f is greater than g for a little while, and then they switch, g is greater than f for the rest of the while, right here, right? Then what I need to do is I need to figure that out beforehand. Maybe I don't have a graph, or maybe I don't have any visualization of what's going on, but I'm just given two functions. If I simply set them equal to each other and find any intersections, then I'll know right away, well, that's not in my interval, I can just do this. Or, that C value where they intersect is in between my A and V interval, I'm going to have to split this up. This is the kind of thing that works like the positive negative. If they switch dominance, is what I call it, if G all of a sudden overtakes F, that's when your integral can start integrating negative numbers. In this situation, if you just integrated from A to B, F minus G, you would not get something that's equal to the area. You would instead be getting a total signed area sum. So we want to avoid that if we're doing area between curves. So what I'll do is I'll find any intersection points and I will split my integrals up. And then I'll do dominance subtractions. F minus G from A to C, right? F is greater than G between A and C. And then G minus F, the one that's on top is now in front. G minus F from C to B. And then I'll add those two integrals together, or however many sections I have. So if I want to do an area between two curves, I simply need to subtract the two functions, top, greater minus lesser, and then integrate on the interval that the top one is greater than the lesser. Quick example. The area between x to the third and the third root of x on the interval -1 to 1. Now, of course, I'm saying these are, like y equals. These are both functions, right? Y equals and y equals. But you get the idea. Here's a graphical representation. X to the third is that swirly looking cubic. The third root of x is the same shape, but more horizontal. It's the inverse of the cubic, right? It's just a sideways cubic. And the area in between them is split into two sections. They intersect 3 times, okay? They happen to actually intersect at -1 and 1, so it's apt that we're integrating from those numbers. But they also intersect at 0. How do we know that? Set them equal to each other, right? Solve that equation if you have to, where it's x to the third equals the third root of x. If you raise both sides to the 3 power, right, you'll have x to the 9 equals x, which you can subtract x to the 9th minus x equals 0, which you can factor x to the 8th minus 1 equals 0. And you'll notice that the only answers that you'll get from this factored equation are 0 from the x and both positive and -1 from the x to the 8th minus 1. Technically, there are 8 answers there, but the other 6, besides 1 and -1, are going to be complex. So we wouldn't use those. So what I'm finding is that they intersect at those points, and 0 happens to be smack dab in the middle. So I set up my integrals accordingly, right? I split the integral from -1 to 0, and then from 0 to 1. And I notice that x to the third is greater than the cube root of x from -1 to 0, and vice versa. Cube root is greater than the third power from 0 to 1. Then I simply need to do both of these antiderivatives. So right here I've got 1/4 x to the 4th minus 1/3 plus 1 is 4/3, 3/4, from -1 to 0. plus, and then this is just going to be the other way around, right? Right here, I'm going to have 3/4 x to the 4/3 minus 1/4 x to the 4 from 0 to 1. Okay, so when I plug in 0, right, both of these are going to zero out. That's nice. Same thing is going to happen over here. When I plug in 0, that's gone. But don't forget, here when this one's 0, I'm going to write it just to remind me. It's 0 minus, right? Top minus bottom. So then I have -1 to the 4th, which is 1 times a 4th. And -1 to the 4/3, which again is 1, because the third root keeps it negative, but the 4th power turns it positive. Times 3/4 is going to give me minus 3/4, like so. Okay, plus. Over here, I've got 0 on the back end, so I don't need to worry about it. It's just going to end up being minus 0 for the latter part. When I plug in 1, I'm getting 3/4 minus 1/4. Over here, notice what I'm getting is negative 2/4, which is just 2/4 or 1/2, right? Plus, same thing here, 2/4, which is 1/2, for a total area of 1. It should make sense to you that I'm getting the same area for these two things because they're completely symmetric curves on a symmetric set of interval boundaries, right? It should make sense to you that I'm getting the same area for both. And notice, because we did this one in the proper order, we actually did come out with a positive number for the area between the two curves on that section. Okay? Let me flip back around for a second and let me comment on this, the alternate way I was asking you to think of this. Remember, what we're doing here is the area between the axis and the curve, right? So if I'm doing the area between two things where something is greater, it's just top minus bottom, greater minus lesser, right? So if it's on the region where f is above the axis, it's just f minus 0, or just f, right? But if I'm underneath, the area between them is what? 0, which is the axis y value, minus the function. In other words, negative f of x. So it's just another way of thinking about how I can get an area out of it, because it's really just the area between two curves, and the axis is actually one of the many curves that we can study. It's kind of a little bit of an uninteresting one, right? Y equals 0 is the x-axis, horizontal line at the y value of 0, but it's still something that can help expand what you understand what we're doing with these definite integrals. Okay, so this is a basic example. Let's get a few more examples of some other regions and possible switches like this. Let's take a look at that example for real. I have y equals x to the 3rd power right here. Let's turn that blue. And then we also had y equals the cube root. I'll just use x to the 1/3 power. You can see me type in the bottom. And yeah, it put it in red for me there. I'll zoom in a little bit more. You can see they do in fact intersect at -1, -1, 0, 0, and 1, 1 here. And I'm actually interested in the area, totally trapped in between them from -1 to 1. I do actually have a command here in GeoGebra that is the integral between function. And I want to show you how it would be a mistake to integrate just blindly from -1 to 1. So I'm going to do function f to function g. Right, that's the ones we have up there. And the starting value -1 to the ending value of 1. As you can see, it does actually shade in both regions there. But look at the total. It is 0. And the reason for that is because it's giving you the total of the integral. It's not necessarily an area calculation. So instead, what I should do is go from -1 to 0. You can see I change it there. And now I've only got the one region here, and it's giving me a 0.5 value. Next, I'll do another integral between, and this time I'll do g then f, right? Because that's the one that's going to be dominant this time is g, from 0 to 1. And you can see it actually shaded in the other region there. And then of course the area total would be those two added together, a plus b, which gives me a total area of 1. Let's start with 3 more obvious areas that we'll be finding between curves. By obvious, I mean if you just draw these out simply, you'll see where they must intersect, like the regions that they have to intersect, even though a couple of them, if you actually had to solve it, would be over the top. Just by drawing these out and just understanding some basic shapes, you can easily find the intersections and things. So these are some straightforward examples. All right, I have the function f of x equals the square root of x, and g of x equals 1 over x. And I want to find the area between these two curves on the interval from 4 to 9. Okay? So first of all, I always want to look for where these things intersect, because remember, if they intersect, they could possibly switch dominance and I may have to split up my integral. Okay? So here I'm noticing that if I draw these out just simply, right, the square root function is this top half of a parabola. The 1 over x is the baseball sideways hyperbola. So I'm noticing that they do in fact intersect somewhere close to the origin, right? Somewhere not too far out on the axis there. And just by visual inspection of what a square root and what 1 over something does, you can pretty much guess it's 1, okay? However, you can also solve for this if you set them equal to each other. This one's not too bad to solve for. Square root of x equals 1 over x. If I multiply both sides by x, I have x times x to the 1/2 equals 1, which tells me x to the 3/2 equals 1. And of course, then I would have to raise both sides to the 2/3 power, but 1 to any power is still 1. So as you can see, they are intersecting when x equals 1. That's this intersection point right here. But my interval was asked on 4 to 9. Okay? So since my intersection point is at x equals 1, 4 to 9 is going to be something more out this way. Like I'm finding the area between them, you know, somewhere over here. Like this much of it. So no big deal. I'm always going to have one function more dominant than the other one for the entire interval, right? So all I need to do is just set up one area integral from 4 to 9. And then, as you can see, the square root is more dominant than the 1 over x. But if it's ever in doubt, in this case, try just plugging in the first endpoint on the interval. The square root of 4 is 2, and 1 over 4 is 1/4. So you can see the square root is already bigger than the fraction. And as x goes on, the fraction's just going to get smaller, and the square root's just going to get bigger. So I can tell that the dominant function is definitely going to be the square root just by either graphical inspection or by number inspection. So I'm going to be doing square root minus 1 over x dx like this. Now don't forget, square root is x to the 1/2. So I'll be doing my integral here. X to the 1/2 add 1 is going to be x to the 3/2. But then that's times 2/3 because I'm going to divide by the new power. Minus 1 over x gives me ln absolute value of x. Don't forget that's a special antiderivative there. And I'm inspecting it from 4 to 9 here. Well, since I'm doing nothing but positive values, I really don't need the absolute value on the ln there. If you write it, it's not wrong, but I obviously don't need it in this case. So then I can start plugging in my values here. If I plug in 9, I'll have 2/3 times 9 to the 3/2. 9 to the 3/2, that's square root of 9, which is 3, but then to the 3rd power, which is 27. Okay, then times 2/3. I've got 2/3 times 27 minus the ln of 9. Great. Minus, now if I plug in the 4, I'll have the square root of 4, which is 2, to the 3rd power, which is 8. So I'll have 2/3 times 8 minus the ln of 4. Okie dokie. From here, 2/3 of 27 and 2/3 of 8. Now I can't reduce the 2/3 of 8. That's going to give me a minus 16/3. The 2/3 times 27 is tempting to reduce because 3 does go into 27, but I'm going to need a common denominator in a minute anyway. So I'm just going to do the straight multiplication. 2 times 27 is 54/3. Now I've got a negative ln 9 and a negative ln of 4, so plus ln 4. 54/3 minus 16/3. Let's see, that's going to be 38/3. Don't forget my equal sign here and here. And I can use my rules of logarithms to help me out a little bit here. ln 4 minus ln 9 would just be the ln of 4/9. And this is going to be the exact version of my answer here. Right? The actual area, let's go ahead and compute that. I've got 38/3 plus the ln of 4/9. 11.8557. Yeah, that'll work. Square units, don't forget, right? Because this is actually the area between those two on that interval. Next example, I have a mixture of an exponential and a linear function. Now, typically, these are not easy to solve type of equations. For example, if I try to straight up just solve like this, I don't have much of a good chance of using any basic algebra to solve this. We have something called a special W function for doing this kind of inverted exponential with a polynomial. We also could do some of the things that are more advanced from calculus 2, which would involve like different infinite series and things like that. So we're obviously not going to be doing that here. This is one of those ones where if you just draw it out, you can visually see that there is an intersection, right? And that's what I have here. 3 minus x is an easy line to draw. And e to the x minus 2 is also an easy exponential. It's just e to the x, which would normally go through 1. and it's been shifted 2 to the right. So it's doing this, but the little center point for the exponential is just a little bit further over. So by visual inspection, I can see that they are going to intersect before this line hits the x-axis. And this line hits the x-axis, obviously, at x equals 3, right? This point right here would have to be x equals 3. So then somewhere between 0 and 3, those are going to intersect. If your torturer is taking it easy on you this day, it's probably going to be a whole number. A lot of times it is. So let's try a few of the whole numbers. Let's just visually try some of these things, right? If I plug in 1, 3 minus 1 is 2, and then 1 minus 2 is negative 1. Is 2 equal to e to the negative 1 power? No, it is not. All right, try the next one out. 2. 3 minus 2 is 1. 2 minus 2 is 0. And e to the 0 is 1. There you go. So the solution to this equation must be when x equals 2. Therefore, that's what this is right here. That's at x equals 2. Well, the interval here that we have is from 1 to 4. 1 to 4 is going to be something like right here, right? It'll be this bit of area all the way up to 2, and then also 4 is going to be way over here. We're going to be getting some more area over this way. But you'll notice the intersection point is right, not in the middle, but right in between the 1 and 4 endpoints that we have. So I definitely have a switch of dominance here, okay? If you want to double check that 3 minus x is greater, just plug in 0. 3 minus 0 is 3, and e to the negative 2 is a very small fraction. So you can definitely tell that the line starts out dominant. But then once you get past 2, right, this line is going to start getting close to 0 and go towards a negative. And the exponential is going to take off very, very fast, like exponentials do. So this one's quite obvious which ones are dominant, and a pretty easy visual inspection on where they intersect. So I'm going to have to do 2 integrals here for my area. My area is going to be the integral from 1 to 2. And the dominant one in that case is the 3 minus x. So I'll be doing 3 minus x minus e to the x minus 2. Next, I'll have to add the integral from 2 to 4, the rest of my interval in question, right? Because I split it on 2. And in this case, e to the x minus 2 is dominant, and it's going to be minus the 3 minus x. But instead of writing it with the complicated, double negatives and things like that, I'll just say it's minus 3 minus x, so it's plus x minus 3. Think about that for a second. All I did was say minus 3 and minus x, right? So they got a little reversal on their signs there. Okay, so now I'm going to do my antiderivatives. I have 3x minus 1/2 x squared. And then e to the x minus 2 has himself as his own derivative and integral. Think about that for a second. The x minus 2, I know it's not x, and it might be tempting to do a substitution there, and if it makes you feel better, go ahead and just section that off and let u equal x minus 2. But you'll see as soon as you do that, that du and dx are equal. And those are some of the ones I warned you that they're really kind of overkill. If you see something on the inside like x minus 2 that has a derivative of 1, then you really can just treat the outside like you would as if you didn't have the inside, right? So the antiderivative of e to the x minus 2 is just still going to be itself. And of course, I'm evaluating this from 1 to 2. Plus, he has himself as his own antiderivative, e to the x minus 2, plus 1/2 x squared minus 3x. And that's going to be from 2 to 4. Let's see now. If I plug in 2, I've got 6 minus 1/2 of 4, so minus 2. And then that's going to be minus e to the 0, which is 1. Minus, if I plug in 1, I've got 3 minus 1/2 minus e to the negative 1. Plus, that's this plus right here. If I plug in 4, I've got e squared plus 1/2 of 16, which is 8, and then minus 12. Roger that. Minus, if I plug in 2. Now, 2 minus 2 is 0. E to the 0 is 1. Plus 1/2 of 4 squared, so plus 2. And then minus 6. Okay, so now I've just got a bunch of arithmetic to do and a little bit of e powers in there, right? So I've got 6 minus 3, and then I'm going to have minus 3 again. So I want you to notice that here, 6 minus 3 is 3, but minus 3 right here. So this and this are going to zero out, leaving me with double negative half and double negative e to the negative 1. So that's 1/2 plus e to the negative 1. I'll write that in something a little bit easier to look at. It's just 1 over e is all it is. Plus, obviously I've got the e squared there and I can't do anything about it. 8 minus 12 is negative 4. And then I've got 3 minus 6, which is negative 3, right? So I've got negative 4 minus negative 3, like that. Okay, so that's going to give me a negative 1 total. So now I've got a grand total of 1 over e plus e squared minus 1/2. Alrighty? And so what would that be approximately? E squared alone is pretty big compared to the rest. Plus e to the negative 1 and minus 0.5. So I have 7.257, let's say. 7.257. I have another one that's, again, if you just graph it out and take a look at the functions, it's obvious where the different functions are and where the intersections probably are and which one is going to be dominant. Okay, so I've got y equals 1 minus x, which is an easy to graph line with the slope negative 1. It goes through 1 on the y and 1 on the x. And then ln x is, your traditional logarithm, ln base e of x, right? So here it is right here. They meet on the x-axis. Okay, the easiest way to see that is ln of 1 is 0, and 1 minus 1 is also 0. So they are obviously meeting here at x equals 1. And the interval we were being asked about is from 1 to 2. So really, what we're doing here is up to 2. And they're just interested in the area between these two above and below the x-axis there, just that little bitty region there. Obviously, my ln is dominant, but if you're not sure, plug in a number bigger than 1, like 1.5. Notice you'll get a negative number here, and logarithms don't give negatives for things bigger than 1, so obviously this is already going to be greater in value, but plug them in and you can see. So my area is going to be the integral from 1 to 2 of the ln of x minus 1 minus x, right? But just like before, instead of writing minus 1 minus x, I'm just going to make that easier on myself by saying plus x minus 1. Just be careful with your ln that you don't get it mixed up with the rest of that piece over there. All right, so now I just need to do the antiderivative. Okay, so if you go back a couple of lectures, we talked about an antiderivative of the ln x. I know that we didn't actually go through any proof right here. I've got a couple of things to show you later in this lecture, but for now, I'm just going to use that antiderivative that we've already talked about. And a is going to be equal to x times ln of x minus 1. And now plus 1/2 x squared and minus x. And that's going to be evaluated from 1 to 2. So let's see. If I distribute this x out right here, I can actually make a couple of things that will consolidate. I'll have x ln x. Notice that this will be minus x right here, and I've already got a minus x, so it's going to be minus 2x, and then I'll still have the plus 1/2 x squared. All that's going to do is just make it a little bit quicker for me to plug in a few things. That's all. Alrighty. Next, plugging in 2, I'll have 2 ln 2 minus 4, and then plus 1/2 of 4, so plus 2, minus, if I plug in 1, ln of 1 is 0, so it doesn't matter what you multiply there, you're going to get 0, minus 2 times 1, and then plus 1/2 of 1 squared, which is just plus 1/2. Alrighty. Notice here that what I've got is right here is -2, and right here is a -2, so plus 2. Those are going to zero out, right? So all of this is going to go with that, leaving me with 2 ln 2 minus 1/2. Of course, you can use, some of your logarithm tricks. You can even bring the 2 in as a power, right? Technically, you could say that that's ln of 4, and then minus the half, if you want to do it that way too. Just don't forget the minus half is not inside of the logarithm, right? This is ln of 4 or 2 times ln of 2 and then minus the half. Either way, you're going to get the same result here. So ln 4 minus 0.5. 0.8863. Alrighty? Time to quickly take a look at these 3 examples. Here was that first one, y equals 1 over x and y equals square root of x. As you can see, they do actually meet at the 0.11, and we were integrating from 4 to 9, and we have a total of 11.86 here for the area that's trapped in between those two. Let me darken it in a little for you. There you go, you can see it better.
It's just this area in between the two curves here. Okay, next we had e to the x minus 2 and 3 minus x. They do actually intersect at 2, and we had to split our integrals into two sections of 1 to 2 and then from 2 to 4. As you can see, the 1 to 2 portion is not very much area, it's 0.87, whereas the 2 to 4 integral is much more, the 6.39, and they total up to the 7.26 for all of the area there. And then lastly, we had 1 minus x and ln x, and we were only integrating from 1 to 2. They do intersect at 1, and then so you're just getting this little weird region here in between those two. Looks kind of like a curved triangle, right?
All right, so now what about ones that aren't as obvious or maybe aren't as easy to graph with enough precision to just start plugging numbers? Or what if graphs meet at some real crazy decimal numbers, right? So you're going to have to be able to do some solving, that sort of thing. And maybe we don't want to have the graphs at our disposal. Let's go all the way algebra and calculus this time without the analytic geometry side. Trig is the best example. These things, they're good on the surface to graph, but if you want any kind of precision, then of course, it takes a lot more work to get the graphs down. And also, being that the trig, works along with the radians and pi's and 2 pi's and pi's over 2, things like that, the intersection points tend to be rather interesting decimals, things that you can't just start plugging and guessing at. Okay, so let's actually dig in here and find the area between these curves here. So here I go. I want to find the area between these two functions on the interval from 0 to pi. All right, so the first thing I'm going to want to be interested in is, where do these things intersect, right? And then, is that in my interval of interest? So that means I need to solve an equation where cosine x is equal to negative cosine of 2x. So I need to be able to solve this equation. And if you've taken a trig course, I'm sure this might look somewhat familiar to you, but there are so many different ways to solve these. And if you have things of this nature where you don't have a lot of shifts and things like that going on, I want to show you an alternate that you may or may not have seen with solving these kinds of equations, something that can save you a little bit of time no matter what kind of setup you've got here. Okay, so notice what I can do is I can get these two on the same side. Cosine x plus cosine 2x equals 0. And this might be something that you've seen in your trig class before, because you've probably done double angle formulas, and you could say, oh, well, cosine of 2x is just 2 cosine squared minus 1, and then I can make a quadratic out of this. Great. But then what about all those other cases where it's weird numbers times x, or if it's even just a 3x here, right? If it's just even a little bit off there, you don't have a lot of those fancy identities anymore. So what I'm going to do is I'm going to introduce you to some of the lesser used identities, the sum to product rules. And the reason why you would think to use this is because I have a sum of two cosines, and you could easily convert this to a product with these identities that I'm about to show you. And if it's a product and it's equal to 0, then I can split things up and solve them immediately, especially if they're just simple sines and cosines that are going to be equal to 0. Okay, so here's an identity for you. Cosine A plus cosine B. Okay, now that's the that's the setup that I have there, right? That's equal to 2 cosine of a plus b over 2 times cosine of a minus b over 2. Okay, now if you're a little skeptical, go Google sum to product trig identities. And if your trig teacher did you any justice, he would have warned you, or she, I'm sorry, they would have warned you that there are thousands of trig identities out there, and it doesn't hurt to be familiar with a few of them. So in this case right here, I have the ability to take this sum and turn it into a product. So this side right here is going to be 2 cosine of, and I've got x plus 2x over 2. Okay, so that gives me 3x over 2, like that. And next, I'll have cosine of a minus b over 2. So that's 2x minus x. So you could do x minus 2x, it doesn't matter. You notice that it could go either way, right? I'll just make it easy on myself. 2x minus x is just x over 2. And that's equal to 0. All I did was I used this identity, right, to turn my sum into a product here. Well, when things are in a product format like that, right, I can just split them and solve them equal to 0. This one is telling me that cosine of 3x over 2 is equal to 0, or cosine of x over 2 is equal to 0. Well, if you remember your cosine values, cosine is 0 at 90 and 270, right? That's pi over 2, 3 pi over 2. But in general, cosine is 0 at the odd multiples of pi over 2. So the way you set that up is you say that the thing inside the cosine here, the angle, right, 3x over 2, is equal to an odd multiple of pi over 2. So to get an odd, you do 2n plus 1, where n can be any number. If you do 2 times any whole number plus 1, I'm sorry, not any number, n has to be an integer. Okay, so that's going to guarantee an odd number. 2 times n plus 1 is going to be odd over 2. If I multiply both sides by 2 over 3, right, flip this, then what I'll get is x is 2n plus 1 over 3 times pi. This is going to give me a whole group of numbers if I just let n be any whole number. Okay? For example, when n is 0, I'm going to get pi over 3. When n is 1, I'll get 3 over 3, which is 1 pi. When n is 2, I'll get 4 plus 1, 5 over 3 pi. When n is negative 1, I'll get negative pi over 3. These are all x values where these two things are intersecting. And of course, as you can tell, there's an infinite number of them by just me letting n be any whole number. Okay, now what about the other side of this or here? This is telling me that x over 2 is going to be equal to 2n plus 1 over 2 pi, right? Odd number, pi over 2. If I just multiply both sides by 2, you'll see that x is 2n plus 1 pi, right? Okay, good deal. And from here, if n is 0, notice I'm getting pi. If n is 1, I'm getting 3 pi. If n is negative 1, right, I'm getting negative pi, so on and so on. I'm seeing a few repeats here, right? See pi and pi, right? That's good. Okay, these are all intersection points of my two functions. These are all x values of intersection points, I should say. Well, we're interested in the interval from 0 to pi. Well, pi is actually one of the intersection points. That's good. I'm ending my interval on an intersection. It's kind of cool. But it goes from 0 up to pi. I have a negative pi. Those don't count, right? 3 pi is bigger than pi, and that's just going to keep getting larger. 5/3, that's bigger than pi also, so that's way out. But pi over 3, that's positive, bigger than 0, but less than pi. So I should also be interested in that particular intersection, pi over 3. Absolutely, I should be. So if I do, say, the cosine, right? Oh, by the way, you should also note that that they're going to be opposites at 0. They do not intersect at x equals 0, right? There is actually one of them that's more dominant than the other, and you can tell right away when you plug in 0. Cosine of 0 is 1, and here this is negative cosine of 0, which would give me negative 1. So you can tell that f of x is going to be on top at 0, okay? So at the beginning, it's f over g. Not in a fraction sense, but f is greater than g at 0, okay? But if you plug in pi, right, then they're going to intersect at that endpoint. At pi over 3, they switch, okay? So by the time I get through the whole interval, it's going to be switched over. Okay? So I've got my interval here, if you want to look at it this way. 0 to pi. And in there is pi over 3. I've got f is greater than g for this section, because when I plugged in 0, I could tell. And then at pi over 3, they intersect. And then if you check it, you'll see g is going to be greater than f. You could plug in just about anything in between pi over 3 and pi. For example, pi over 3 is something a little bit bigger than 1. Pi is something a little bit bigger than 3. The number 2 is in between there, right? If I plug 2 into both of these, cosine of 2 and negative cosine of 4, so that you'll see what I'm saying. Cosine of 2 is negative 0.4. And negative cosine of 4 is 0.65. So you can see on this second interval here that g has taken over dominance, right? Okay, so what does this mean? It means I have two different sections that I need to integrate in order to get my area going here. So let's do that. I'm going to integrate from 0 up to pi over 3. And I'm going to be doing f minus g. So that's going to be cosine plus cosine 2x dx. Because I'm doing minus a negative. Okay, and then, of course, don't forget your dx. Plus integral from pi over 3 to pi the other way around. Negative cosine 2x minus cosine x dx. So I've got my two integrals set up and ready to go. Let's do some antiderivatives now. Antiderivative of cosine x is sine x plus antiderivative of cosine 2x is going to be 1/2 sine 2x, right? Remember we did the constant multiple rules with a lot of our exponentials and trig functions. If I'm do a derivative, it multiplies by the 2, but I'm doing an antiderivative, so it divides by the 2. And that's going to be from 0 to pi over 3 plus, and I've got a negative now. So when I antiderivative, that's going to be negative 1/2 sine 2x minus sine x. And that's going to be from pi over 3 up to pi. Right? Now, let's start plugging in some values. if I plug in pi over 3 for sine x, sine of pi over 3 is sine of 60 degrees. I'll just go ahead and make some room down here. Square root of 3 over 2 plus 1/2 times sine of 2 pi over 3, right? That's sine in the second quadrant. With a reference angle of 60, though, it's also going to be square root of 3 over 2. And then for 0, sine of 0 and sine of 0 is 0, so I'm really just doing minus 0 there. Plus, here when I plug in pi, sine of 2 pi is 0. And when I plug in pi here, sine of pi is also 0. So this is going to 0. I've got 0 minus. And now I'm going to plug in the pi over 3, right? So I've got negative 1/2 sine of 2 pi over 3. Square root of 3 over 2, right? Minus this one, square root of 3 over 2 again. Nice. So then what I have here in total, if you look at this as I could factor out the square root of 3 over 2 here, times, it's 1 plus 1/2. Of course, these zeros aren't there. This negative makes both of those negatives go away. And then I'm left with plus square root of 3 over 2 again, times, and it's going to be 1/2 plus 1 again. So I've got 3/2 and 3/2. I can obviously factor the square root of 3 over 2 out of both of those, which is just going to give me a grand total of 3 here, because this will be 6 over 2. 3 times square root of 3 over 2 for the final area value there, right? Which should be a little intriguing to you because the interval was not split in half, right? The interval was split by basically a third and then 2/3 on the other side, and yet the two integrals came out symmetric areas with those two, right, in between the curves. Sort of interesting the way that can happen. Let's get a decimal rolling for that just in case. 3 square root of 3 divided by 2. 2.598. Okay, so next example over here, I can follow something quite similar. I need to figure out where these two functions intersect. So I'm going to be setting it equal to each other. And 4 sine pi x over 3 is going to be equal to 4 cosine pi x over 2. And the real difference here is that first they're different trig functions this time, sine and cosine, still related, but also their frequencies are different, right? The pi over 3 and the pi over 2 are different. I can immediately divide away the 4's, right? Divide both sides by 4 and that's gone. And what I'm going to do is very similar to the tactic I did over here, just with a couple of extra steps. I'm going to subtract this over. So I've got sine of pi x over 3 minus cosine pi x over 2. Now if you look up your list of sum and difference converting into products, you won't find very many that have a sine and cosine on the summing side mixed together. That's okay. I can fix this pretty easily by converting cosine with the fact of using the cofunction identity. So here's the first identity that I'm going to use. The cosine of some value b is equal to the sine of pi over 2 minus b, like this. That's the cofunction identity. So then right here, sine of pi x over 3 minus sine of, it's pi over 2 minus pi over 2x, right? Because it's pi over 2 minus whatever my angle was to convert from cosine into sine. So then from here, notice, by the way, it's equal to 0 in both of these instances. Now I've gotten to a point where I have two sines together in a subtraction. And so what I would look up is the sum and difference into product. Sine A minus sine B is equal to 2 cosine A plus B over 2 times the sine of A minus B over 2. Cosine A plus B over 2, sine of A minus B over 2. Right? Okay. So then, what is this going to do for me? I can take these two and convert them here. So I'll have 2 cosine of, I'll have A plus B. So that's pi over 3x plus pi over 2 minus pi over 2x all over 2. And then sine pi over 3x minus, now it's minus this, right? So what's going to end up happening is I'll just do the plus with a reversal. Pi over 2x minus pi over 2 all over 2. And this is all going to be equal to 0. Now that may seem rather complicated for you, okay? But if you just pick it apart, it's actually not. What we're doing, again, just like last time, is I'm going to be setting a cosine equal to 0 and a sine equal to 0. And what this is going to do is have some easy fallout, because cosines and sines equaling 0 by themselves either happen at whole pies or half pies. Okay? So right here, the fact that this is a multiplication and this is a multiplication right here, the 2 is essentially, gone. It's useless. Just like the one over here is essentially, useless. But cosine is equal to 0 tells me that pi over 3x plus pi over 2 minus pi over 2x all divided by 2. It's a cosine. Where's cosine equal to 0? That's the 2n plus 1 pi over 2. Okay? It's equal to the odd pi over 2 multiples, just like we were talking about before. Sine is equal to 0 at the whole number pi equal to 0 multiples. So that means here, pi over 3x plus pi over 2x minus pi over 2 all over 2 is equal to just n times pi. Just some number n, whole number, times pi. It could be 0, could be 1, could be 2. The ones from the sine are nicer in that sense. Okay, so first thing I notice is that everything has a pi. I can also multiply both sides by 2 here to get rid of those in this particular equation. But everything is times pi. So if I divide by pi, all of the pi's go away. That's nice. What that's going to leave me with is 1 over 3x minus 1 over 2x plus 1 over 2 is equal to 2n plus 1. So that's 2 6 minus 3 6 right here. Okay? For a total of negative 1/6 x is equal to, right here I'm going to have 2n plus 1 minus the half that was over there. I'm going to multiply everything through by negative 6. So I've got negative 12n. I've got negative 6 plus 3. Right? So that's minus 3. Negative 6 plus 3. Okie dokie. So, what am I looking at here? X is equal to negative 12n minus 3. This is something that can give me different values of x that I can use as solutions, right? For example, when n is 0, right, I can get negative 3 as one possibility. When n is negative 1, that would be negative 12, which is 12, minus 3, which is 9, right? What else? I've got, I could do positive 1, right, which would give me negative 15. I could do 2, which is negative 24, minus 3 is negative 27. I could do negative 2, which would give me 24 minus 3, which is 21. Okay, so these are all possible x values where those two are meeting. That gives me an entire list of them to try out. All right, next, right here, I can do something very similar. I'm going to multiply both sides by 2. So that's going to give me 2n times pi. But I'm going to divide everything by pi again, so the pi's are going to be gone. So after I multiply the 2, I'm just going to have 2n. And right here, I've got 1/3 plus 1/2 on the x's. And then I've got minus the 1/2 here. 1/3 plus 1/2 is 5 over 6x. And if I add the half over, I have 2n plus 1/2. Okay, so I multiply everything by 6. And I've got then 5x is equal to 12n plus 3. And then divide by 5, right? Divide by 5. So again, I've got something where if I plug in different whole numbers for n, I'll get all of the different locations where these sinusoidal waves are intersecting each other. So for example, when n is 0, I'm getting 3/5. When n is 1, I'm getting 15 over 5, which is 3. Okay? When n is negative 1, I'm getting negative 12 plus 3, which is negative 9/5. What about when n is 2? That's 27/5. Okay, so on and so on. These are all different values that I'm interested in because they're going to be the intersection points that could affect my intervals. Well, let's see. I'm trying to get the area between them from 1 to 4. Well, let's see. Negative 3 is outside of that. 9 is on the other side of it. All the negatives are too far over 21. So none of these are any good. Well, I shouldn't say they're not any good. They're just not in my interval. 3/5 is less than 1, so no. 3 is in between 1 and 4. Absolutely. And then negative 9/5, 27/5, that's bigger than 5. So it looks like 3 is going to be the only one that that will exist on my interval that I'm interested in. Okay, so let's split accordingly. First of all, we need to see which one is dominant when. I've got my interval from 1 to 4, and I'm splitting it with a 3. So I've got my two intervals. Where do they start out in dominance? Well, let's see. If I plug in 1, right? If I plug in 1, I've got sine of pi over 3 times 4. Well, they're both times 4, so really I'm gonna compare the sine and the cosine value, right? The cosine value is going to be 0. because pi over 2 times 1 is pi over 2. Cosine of pi over 2 is 0. Sine of pi over 3 is, again, the sine of 60 degrees, so square root of 3 over 2. It's a positive number, which is greater than 0. So here, A is dominant over B. More than likely, when they intersect, they switch. There are a few cases where, of course, they wouldn't, because sometimes when two things intersect, they might just intersect in a hill, right? And one of them may stay more dominant than the other one. Who knows? Okay, so let's double check on the other end with 4. Let's say sine of 4 pi over 3 is going to be a negative because 4 pi over 3 is past pi, right? So sine of 4 pi over 3 is going to be a negative, whereas cosine 4 times pi over 2 is 2 pi, and cosine of 2 pi is 1. Okay, so we can see that this is going to be a large positive number, whereas the sine at 4 pi over 3 is going to be a negative. So we can definitely tell at this point that B has taken dominance over A. Okay, so let's use that information to our advantage now, and let's calculate our area. I'm going to do the integral from 1 to 3 of 4 sine pi over 3x minus 4 cosine pi over 2x. And then, of course, from 3 to 4, forgot your dx, plus integral from 3 to 4 the other way around, right? I'll have 4 cosine pi over 2x minus 4 sine pi over 3x dx. Lovely. Equals. I'm going to factor the 4 out. See how they both have the 4? I'm going to pull that out basically of everything, right? Because everything has the 4 here. So I'll be doing 4 times. And then the first antiderivative here, I'm going to have sine go up to negative cosine, so negative cosine pi over 3x. And of course I'll have to divide by the multiplied number there, so that's 3 over pi when I divide by the number. Minus cosine, so that integrates again to minus sine pi over 2x. And of course that would then give me 2 over pi times that sine pi over 2x. And that's going to be from 1 to 3. Good stuff. Plus, I seem to be running out of room here, so I'm going to move it down to here to try and squeeze it in. So plus basically the same two antiderivatives. So I have 2 over pi. Cosine goes to sine pi over 2, and then minus negative sine goes up to plus cosine. 3 over pi cosine pi over 3x, and that's going to be evaluated from 3 to 4. Close my big parentheses, that was times the big 4. Now I want you to look also really closely. These pi's out here are just multiplied on the outside, right? So I'm also going to be able to save myself a little headache by factoring out those pi's. Okay, so I'm going to take those out to the very front, and I'll have 4 over pi out at the front of the whole thing. Okay. 4 over pi in the front. Now, if I plug in 3 to this guy here, remember I factored out the pi, okay? So 3 over 3 is 1. Cosine of pi is negative 1 times negative 3. So I've got 3. Here, if I plug in 3, I've got sine of 3 pi over 2, which again is negative 1. Sine of 3 pi over 2 is negative 1 times negative 2. So I've got plus 2. Minus, I'm going to plug in 1, right? So that's going to be negative 3 times cosine of pi over 3, which is 1/2. Next, when I plug in 1, I'm going to have negative 2. And then I'm going to have sine of just pi over 2, right? 1 times pi over 2 is 1. So it'll look like that. Plus, right? Plus, I'm going to have 2 sine of 4 times pi over 2 is 2 pi. Sine of 2 pi is 0, right? So 0. And then I'm going to have 3 times cosine of 4 pi over 3. Cosine of 4 pi over 3 is in the third quadrant, so the cosine will be negative, and I'll have plus, so minus 3 times. The cosine of the 4 pi over 3 is just like the cosine of pi over 3, but in that quadrant with the negative. So that's also going to be 1/2, like this. Minus, if I plug in the 3, I've got sine of 3 pi over 2, which is negative 1 times 2. I'm going to put it here, minus negative 2. And here, if I plug in the 3, I'll have cosine of pi, which is negative 1 times 3, which is minus 3. Like that. Alrighty. So let's see what we've got. First thing I've noticed in this whole thing is that I'm going to have a positive 3 over 2, and I've got a negative 3 over 2. So immediately those are going to go away. And I'm also noticing that I have a 5 plus another 5 here, which is going to be 10, and then plus another 2, which is going to be 12 times 4. So let me write it out. I've got 12, right, for that whole thing. So what I have is 48 over pi, which is approximately what? Divided by pi. 15.27887. We'll just say around 15.3. Let's just do that. I know I've been doing other longer decimals before, but really on a graph, how would you notice much different than a single decimal anyway? Okay, I know these are rather involved problems. I hope that this has shown you another way of thinking about solving trig equations, and also being able to keep track by just using some equal to 0 properties of cosine and sine. By keeping track, I mean noting when you're going to have all of these multiple intersecting points.
So let's take a geometry look at these two problems. The first one was y equals cosine x, and y equals negative cosine of 2x. As you can see, they have several points where they intersect. Just in our view here that we can see, of course there's an infinite number total, but you can see where they do actually intersect. And we were interested in the interval from 0 to pi. And of course, just as we calculated, they do actually intersect at pi, but they also intersect at pi over 3 in between. And our two integrals were the first region from 0 to pi over 3, and the second region from pi over 3 to pi are these two areas here. And you'll notice they are actually equal. They're both around 1.3-ish. And of course, area total would then be the 2.5981 we were talking about from these two regions. Okay, and then the other problem that we had was the 4 sine pi over 3x and the 4 cosine pi over 2x. And as you can see, again, just like the other one, they're two sinusoids that intersect in several locations. Right? You can find, well, actually, we can even find another one right here too. Right here. So we were only interested in the region from 1 to 4, though, right here. The integral from 1 to 4, this region, that adds up to 10.8225, and this region here that adds up to 4.45 is the interval from 3 to 4. As a total, they have the 15.2789 that we talked about.
Time to expand our horizons a little bit here. So ever since the beginning, you've been shown that integrals have to be an area between the x-axis and some function. What we're going to start now is a long drawn-out process that'll go all the way through the next calculus course in an attempt to break you free of what you've been told are the restrictions of being a function. Eventually, what we would like to be able to do is to study any curve and any region between any 2 or 3 or multiple whatever curves. And you basically want to be able to do whatever you deem necessary. So we're going to have to expand our understanding and expand our horizons on what it means to integrate, what it means to have a function that represents a curve. And this is a good place to start so that you can get some other experiences with integration. Integration does not have to be along the x-axis. Okay, so step number 1 to realizing that we can make functions work in multiple different ways is to realize that the y-axis is a enumerated list of counting objects as well. And I can take any integral that I would like and convert it from a x counted interval to a y counted interval. And the way you do this is you simply reverse what the relationship is showing between x and y, right? If I have something where y is equal to f of x, then I just reverse that around, and instead of having y by itself, convert it to having x by itself. X equals some function g of y. Make sure it's the same curve, but then when you integrate in terms of x, you're using a delta x with rectangle, and you're stacking a bunch of them together. The heights of those rectangles are values of your function f of x. The exact same concept can be counted a different way. Instead of lining rectangles up vertically, I can stack rectangles horizontally, and the width of the rectangle can be a delta y, and then the width right here, the actual girth of the rectangle here, the breadth of it, can be from the function g of y that has the relationship, the same relationship between x and y as the f of x between y and x over there did. It's the same curve, but instead of counting vertically f function values, I will be counting horizontally g function values. Okay, it amounts to the same thing. And all I'm doing is switching to a dy eventually, because that's what delta y will become as you let it shrink, right? I'll be using a dy instead of a dx. And that's the major difference here. So let's start with something like this. If I have the function y equals ln of 4 minus x, Okay? That's a logarithm that points to the left because of the negative. It has a vertical asymptote at 4 because of the ln of 0 is undefined. And it goes through the x-axis at 3, right? Hooks to the left like that. I'm interested in the area between the y-axis, the x-axis, and this curve, y equals the ln of 4 minus x. So then one way I could do this is I could integrate from 0 to 3 ln of 4 minus x, the function, right? Just everything between the x-axis and the function. That's if you want to stack your rectangles this way. Okay? However, if I convert this equation right here by solving for x, to do that, I can take an exponential of both sides. That would be e to the y is equal to 4 minus x. And then adding x and subtracting e to the y, I can note that x is equal to 4 minus e to the y. So this relationship and this relationship are the same one. That's the same curve, just written in two different functional formats. So if I convert it to this other format, it still gives me the same points on this red curve here. But since I'm counting an x value, it's like my rectangles are being laid horizontally, and I'm giving an x value based on the curve, right? X is now calculated every time I pick a y. Y is the input, x is the output. So every time I pick a y value, I will get an x value that gets me out to the curve. So then I'll just be stacking those up. So what I really need to know then is, where does my y value start? Obviously the axis, so the y value would start at 0. And then where does the y value end? That would be this intersection point right here. Well, that's when x is 0, right? When x is 0, I have the ln of 4 minus 0, which is just ln of 4. So I'll be going from 0 to ln of 4. That's y equals 0 to y equals ln 4, not x, y. And my function is 4 minus e to the y, dy. Now, yeah, sure, there's a ln4 function, not function value, a y value here, right? But this particular antiderivative is easier than that antiderivative, isn't it? This antiderivative here needs a substitution of -1 du, right? Because the if I let u equal 4 minus x, okay, right here, if I let u equal 4 minus x, du would be equal to negative dx. That would cause me to need to do this, the integral of negative ln u du, right? And of course I could just pull the negative outside, like so. And then when x is 0, u is 4. And when x is 3, u is 1. Okay. I'm going to take advantage of the fact that if I flip my limits, it does the opposite. So basically I'll get rid of this negative by reversing the limits. And the antiderivative of ln of u is u times ln of u minus 1. I'm going to evaluate that from 1 to 4. Notice I switched, right? 1 to 4. That's why the negative isn't there anymore. Okay? Let me split this up here. So look, right here, if I plug in 4, I'll have 4 ln of 4 minus 1. Or I'll just do minus 4, like this, equals, because I'm just going to distribute it, right? 4 times ln 4 and 4 times -1. Minus, if I plug in 1, I'm going to get 1 times 0 is 0 minus 1 times 1 is 1. Okay, so I'm getting 4 ln of 4, and then I've got a minus 4 plus 1, so minus 3. Okay, so I'm getting that value there. Let's do this integral down here, the one that is done in the y direction, right? I'm doing a delta y, which means my rectangles are horizontal instead, right? So a dy. And all I had to do was reverse the equation to solve for x. And then I just needed some boundary values that represented the very bottom and the very top of where I would be stacking my horizontal rectangles. So let's see. I'm going to have 4y minus e to the y is its own antiderivative. And I'm going to evaluate that from 0 to ln of 4. So when I plug in ln of 4 here, I get 4 ln 4 minus e to the ln 4. I hope you're recognizing that since those are the same base, those go away, and I'm going to have just a value of minus 4 there. Minus, if I plug in 0, that's 0, and then e to the 0 is 1. See any resemblance in the crunch out here? I'm still getting 4 ln 4, and I'm getting negative 4 plus 1, so minus 3. Except that this particular integral was a bit easier to do the antiderivative of. I didn't have to do a substitution in this case. Now that may not always be the case, but the point is there is another way to add up these integrals. I can use y as my independent and x as my dependent instead if it happens to manipulate the equations in a way that makes my integrals more convenient, right? Maybe you didn't remember that the antiderivative of ln u is u ln u minus 1. We didn't exactly go through a proof of that one either. However, you can use this particular method reversal to show that that is the antiderivative, because it's not a coincidence, as you can see, that these came out to be the same. All right, let's go again. Right here, let's say I've got the curve y equals x to the 2/3, and I want to cap it at y equals 4. So I want the area in between those two, right? I want the area in between y equals 4 and y equals x to the 2/3. Well, from what we've been doing, since it's in between those two curves, I have to do the top curve minus the bottom curve, 4 minus x to the 2/3. And I would have to integrate from 0 to 8. Why? Because that's where they intersect, right? Here, if I set these two equal to each other, you'll see x to the 2/3 is equal to 4. Whenever I do the 3/2 power of both sides, right? This is going to be a 3/2 power, which is square root of 4 is 2 to the 3rd power is 8. Okay, so you'll notice that the y value is 4, but they intersect at an x value of 8. Well, all right then. If I do this antiderivative, I had to do top minus bottom. Okay. Antiderivative is 4x minus 2/3 plus 1 is 5/3. And then I have to divide by the new power, so 3/5. From 0 to 8. Of course, if I plug in 0, these are both 0, so I'm not worried about that. If I plug in 8, I've got 32 minus 3/5 times 8 to the 5/3. 8 to the 5/3 is 2 to the 5th, which is 32 again. That's 1 times 32 and 3/5 times 32. So 1 minus 3/5 is 2/5 times 32. So 64/5 fifths is the region in between those two curves. Well, alrighty then. Next, let's talk about another way that I could have done this. If I wanted to stack, I'm first of all noticing that it touches the y-axis here, right? Having contact with the y-axis means I don't have to do an integral between two curves. It means I can simply stack my rectangles from the axis like a normal integral of just one curve would be. And what would that curve be? It would be the blue curve here, the y equals x to the 2/3, and I'll just be stacking my rectangles horizontally instead. Okay, so what does that mean? I need to solve that in the other direction. In other words, I have y equals x to the 2/3. The reverse equation would be me putting the exponent on the other side by reversing it. That would be y to the 3/2 is equal to x. Okay, so I'm integrating, as you can see, y to the 3/2 times dy. That's how I do my horizontal rectangles. I simply convert to the opposite relationship and I use dy with the y. Okay, now how do I know 0 to 4? Well, you can see right away that the bottom point here was at 0 because this one was at 0. And we already said the upper cap was y equals 4. So I only need to do a single integral this time, which means I'll be doing 3/2 plus 1, which will give me y to the 5/2. Of course, I have to divide by the new power, which will give me 2/5. And then I'll be evaluating this from 0 to 4. Right? If I plug in 0, I get 0. But if I plug in 4, I've got 4 to the 5/2. That's the square root of 4, which is 2, to the 5th power. So I have 2/5 times 32, because that's 2 to the 5th, which, as you've already seen, is 64/5. Okay? So that's how we integrate in the y dimension instead of the x dimension. If you've already got a relationship for a curve, if it's something that you can invert like that, especially something that'll invert quickly and easily, and you also know where you can reverse the limits and make sure you're getting y values instead of x values, then this could actually be sometimes a different and sometimes better way to integrate some of these regions that we're going to find areas of.
Here's that first example just so that you can see the area of the region that's being graphed there. And then let's take a look at the second one. Here's those two graphs. We have y equals x to the 2/3 here, and we have y equals 4 as the cap. The thing you need to notice is if I rewrite the function as x equals y to the 3/2, when I click on, you can't see it because it's actually on top of this curve. But do note that when you do rewrite it, it's possible sometimes that you have to change the region of your function. Here, I'm only going to get the right part, and that's okay. When I integrate, it equals the same value that we got before.
Okay, so let's finish up with a couple of examples of when I may want to actually convert into dy. One of them on one extreme and one of them on the other, where it is really good sometimes and sometimes not. But they're both going to be examples of how switching to dy can consolidate potential workload. It doesn't always consolidate all of the workload, but anyway, so here, I want to find the area that's trapped beneath this line, beneath this parabola, and above the x-axis. The line y equals x over 2, the parabola y equals the square root of 8 minus x, and the x-axis. So what you may notice is if I do this the traditional way, by dx by adding up from left to right on my x-axis. And if I have my rectangles vertical, then it's just two separate normal integrals. If I'm doing it the traditional way, I don't actually have to integrate between two curves, between two functions, because it's just x-axis to line, x-axis to line, x-axis to line, and then it switches x-axis to parabola, x-axis to parabola, x-axis to parabola. So I can just integrate the line on one part and integrate the parabola on the other part. All I need to do is find that intersection point. So to find that intersection point, I would just set them equal to each other. X over 2 is equal to square root of 8 minus x. Square both sides. Multiply everything by 4. Go ahead and shift everything over. And then from here, I'll be able to factor. You can see that I'll have x plus 8, x minus 4. And I'm getting two solutions here of negative 8 and positive 4. Obviously, this one would have to be at positive 4 right here, because negative 8 is going to be way over here. And the reason we would even have that other solution, this is the one we want, the reason why we would have the negative 8 possible solution is if you had the parabola looping all the way back underneath, if you had both halves of the parabola, and it would hit way down over here where the line and the parabola would meet up again, which would be at negative 8. But we found ours to be at x equals 4. So that's what this is going to be right here. I could actually split that into two integrals. It would be the integral from 0 to 4 of x over 2 dx, and the integral from 4, where does this intersect at? Where x is 0, so it would be, not where x is 0, where y is 0, I'm sorry, so it would be 8. Integral, square root of 8 minus x dx. So this would be the traditional way to set that one up. Okay, split it into the two regions and integrate that way. But if I wanted to consolidate these two integrals into a single integral, I could actually switch into the dy, integrating into the y dimension. That would cause my rectangles to go horizontal. If my rectangles were horizontal, notice that at every level, every y value I pick, I would be stacking between the same two objects every time. It would go from line to parabola, line to parabola, line to parabola. Every single one of my horizontal rectangles would be between the same two objects. So I wouldn't have to switch anything. I would just need to know what's the lowest y value, what's the highest y value, and then I would need to write both of these curves in terms of x, right? I would need to solve these. So let's do that. I need y equals x over 2. That would easily convert into 2y equals x. And then y equals square root of 8 minus x. I could convert that by squaring both sides and then adding an x and subtracting the y squared. So x would equal 8 minus y squared. All right. So now I'm set up to integrate in the other way. So I could say, or I could have the integral of, now remember, whenever we're doing the area between two curves, it's always greater minus lesser. In the field of doing the horizontals with the dy, that would be right minus left, because I'm further down the x-axis, more positive if I'm to the right. So if I'm in terms of x like this, then I would go right curve minus left curve. So my right curve is 8 minus y squared. That's the parabola. minus 2y, which is the left curve, the line, dy. Okay, and then of course my stacks build from bottom to top, right? I want to count in the positive y direction, so from 0 up to wherever this intersection is, right? That's the top point of the area that I'm integrating here. Well, if this happens at 4 for the x, right? 4 divided by 2 should be 2 for the y, should be at 2. So I'm going to go from 0 to 2. And now I've got this integral as a single integral, and it doesn't have a radical that would require some sort of substitution. Okay, so I won't be doing this integration. That seems like a lot more work. Plus, the whole point of this scene, right, is to show how I can integrate with the dy. So let's do that. Okay, so here I'm going to do my antiderivative. That's going to be 8y minus 1/3 y cubed of minus y squared from 0 to 2. Of course, if I plug in 0, everything in this particular case zeroes out. If I plug in 2, I've got 16 minus 8 over 3, because 2 cubed is 8, minus 2 squared is minus 4. So then that gives me 12 minus 8/3, which is 36/3 minus 8/3, which gives me 28/3 for my integral there, for my area. All right, so definitely a lot less work for this particular integral than trying to do these two separate ones, and one of them also being more complicated. All right. Now, it doesn't always work out that way, as my next example will show you, but you can pretty much most of the time convert into dy, and very often it can convert something that is two integrals into one single integral. So then let's look at this one. This is one that I picked up from looking at some of the online software that's related to OpenStax, and it looked like a problem that was the same type, but definitely on the other end of the difficulty level here. Mostly just because it just looks weird when you convert some of these functions. But these are definitely things that you want to be able to practice and know that you can do. Okay, so I'm gonna look at this first from the x direction, and we're gonna see what that would look like. But we're gonna switch it to the dy, and no matter how yucky it looks, we're going to integrate the dy integral. Okay, so first I'm looking at the region between this parabola and this line between 2 and 4. The parabola here has x-intercepts at 1 and 2. You can see that quickly from factoring, that this would be x minus 1 times x minus 2. And the line has an x-intercept of 4, right? That would give me 8 minus 2 times 4, which is 0. And I want the area trapped between them and above the x-axis. So just like before, if I integrate dx, right, if I integrate this way, dx would be the vertical rectangles, I would need to know where their intersection point is, because I could actually split this into two pieces, right? So I'm interested in this intersection point right here. To find that, I'm just going to set them equal to each other. 8 minus 2x is equal to x squared minus 3x plus 2. Right? So then to solve a quadratic, I just get it equal to 0. I would be adding, so that would give me negative x, and subtracting 8 from both sides would give me minus 6. This can be factored into x minus 3 times x plus 2. So then my two intersections are x equals 3 and x equals negative 2. Therefore, this intersection point happens when x equals 3, right here. And the negative 2 must be this intersection point over here, right? That must be x equals negative 2. We don't need that one. We're interested in this one, right? And then what y value goes with that? If I plug x equals 3 into here, you'd see that would give me 8 minus 2 times 3, which is 8 minus 6, which is equal to 2. So it is actually equal to this point right here. So this is the point 3 comma 2, this peak point right here. All right, so then old school integral setup, if I were to do that, I would have the integral from 2 to 3. And notice that's completely underneath the parabola. So that would be x squared minus 3x plus 2 dx plus the integral from 3 to 4 of the line 8 minus 2x dx, right? Because it's completely underneath the line there. All right. So that would be the old school way of doing it. And notice that those two integrals are particularly not very bad, right? I could whip out a couple of power rules on that one and easily just knock out those two integrals. But that's not our point here. Our point here is we want to see what it looks like in the y realm. So I notice if I'm going to do dy and I'm going to stack my rectangles horizontally, then I'm going to always be going from the parabola to the line. See, parabola to the line, parabola to the line, parabola to the line. Over and over and over again, those would stack up, okay? And then, of course, my y values would count from bottom to top. So my y values are going to go from 0 up to 2, right? Coincidence, not always the same as the last one. Okay, so to do that, I need to have both of these where it's x equals, okay, so that I can have the function of y to integrate. So let's solve these two. This one right here, if I add the 2x, subtract the y, and divide by 2, 4 minus 1/2 y. Okay, so I have that one solved for. This other one right here is a quadratic, and unfortunately, the only way that you're going to solve for x on that one is the quadratic formula. And here's y, pun intended. I'm going to need a 0 for the formula to work. So I'm going to move the y by subtraction like this. And then I'm going to notice that my a is 1, my b is -3, and my c value is 2 minus y. So if I set up the quadratic formula solution, that's x equals -3, so 3, plus or minus square root 3 squared, which is 9, minus 4 times a, so 4 times 1 is 4, times c, which there's my c, and then it's all over 2 times a, so 2 times 1 is 2. Okay, so then I've got x is equal to, I'm going to split the 2 underneath. That's going to give me 3 over 2 plus or minus square root of 9 minus 8 is 1. And then I've also got -4 times -y, which is plus 4y. And this is also over 2. Okay, so I've got x by itself, but I've got a plus and a minus. Don't forget that I have a parabola here which has 2 symmetric sides. The middle is right here in between 1 and 2 at 1.5. If I am greater than the middle, then I should take the plus. If I'm less than the middle, I should take the minus. As it turns out, we are to the right of the middle of the parabola, so I'm going to be taking the plus as my, right? I'm going to use the plus, not the minus, for my curve, for my function here. Okay, so that means I can set it up in one integral. I'm going to integrate from 0 to 2. Those are y values. Y equals 0 to y equals 2. Y, right? 0 to 2 on the y-axis. And it's right minus left. So it's the line minus the parabola. Okay, so that's going to be 4 minus 1/2 y minus 3 over 2. It was plus, right? I'm subtracting the whole thing. So minus square root of 1 plus 4y over 2 dy. All right? I'm going to start off by making the integral a little bit easier on me by factoring out a 1/2. Okay? To do that, this 4 I'm going to have to think of as an 8 over 2. Okay? 8 over 2, 1 over 2, 3 over 2, radical over 2. I'm going to factor that 1/2 out. And it's going to be integral from 0 to 2. I have 8 minus 3, which is 5. And then I've got minus y. And I've got minus the radical. 1 plus 4y dy. Now I notice that I can integrate the 5 and the y right now. So I'm going to go ahead and do that. But then I'm going to be doing the antiderivative of all three of these pieces, but the antiderivative of the radical is going to have to stick around for a minute because that one needs a substitution. So let me make a little space here. Dy. I'm going to have 1/2. Antiderivative of 5 minus y is 5y minus 1/2 y squared. And notice I still have minus 1/2 integral 0 to 2 of square root of 1 plus 4y dy. Oh, and yeah, this is 0 to 2. All I did, remember, with derivatives and antiderivatives, I can take each piece that's added and subtracted separately. I didn't want to overcomplicate something that was already simple for me with the 5 and the y, just because I had something way more complicated with the radical. Okay, so I went ahead and did those two antiderivative pieces, and I can go ahead and just separate that number piece out and have those done. But I still have the minus 1/2 times the integral with this guy. Okay, so let's consolidate this one. If I plug in 0, I get 0, so that piece is gone. And if I plug in 2, then I have 1/2 times 10 minus 2 squared is 4 times 1/2 is 2, like this. Minus 1/2 integral from 0 to 2 of that square root of 1 plus 4y dy. Okie dokie? Okay, so then to do this integral, I'm going to use a u substitution. That u substitution that I'm going to use is going to have u equal to 1 plus 4y. And I'll go ahead and write this to the 1/2 power. Like that. Of course, that means du needs to be 4 dy. And I don't have a 4 dy, but I can easily get one, right? If I multiply by 4 and if I divide by 4 also. So let's see, let me make a little space right here. The minus and the 1/2 are still there. But notice I'm multiplying by 4 to do my substitution, so I'm also dividing by 4 on the outside. 4 dy is going to allow me to substitute here. Okay, so real quick, this is 8 times 1/2, which is going to be 4, minus 1 over 2 times 1 over 4 is 1 over 8. And I have the integral of u to the 1/2 du. And I need to convert my limits, right? When y is 0, I have 1 plus 4 times 0 for u, which is 1. And then when y is 2, I have 1 plus 4 times 2, which is 9. All right. So my substitution is complete. I can do my antiderivative now. 4 minus 1/8 times, u to the 3/2, I add 1, right, to the power, divide by 3/2, which is 2/3, and then that's evaluated from 1 to 9, right? So then I'll be plugging in my two values. That's going to be equal to 4 that was already there, minus 1/8 times, if I plug in the 9, that's square root of 9 and then cubed. So I have, let me factor out the 2/3. That's going to give me 27. And then if I plug in 1, minus 1. See, I just took the 2/3 out to make it easier to plug in the numbers. The 8 and the 2 are going to reduce also, which will give me a 4 times 3 in the bottom is 12. So I have 4 minus 1/12 times 26. Let's see, that's going to be 4 minus 26 and 12 will reduce also. That's going to be 13/6. 4 is 24/6 minus 13/6 for a total of 11/6. Okay, so let me just reiterate. This area probably would have been a lot easier to find the X route, but the whole point was we can put this in the dy dimension. I can actually find it with a single integral that had multiple pieces, of course, just like any integral can. You will get the same answer either way. Sometimes it's not as good to convert, right? Because this one actually created a radical for me to have to mess with. Whereas last time it got rid of a radical for me, okay? So whenever you're in one of these situations, it's best just to look at both setups fully and see, is it gonna be a lot more work with those radicals, or would it be something that's gonna help me out by consolidating and making it one integral? You know, you just gotta look at both routes, okay? So I hope this whole video has helped you understand a more broader range of how we're finding areas using integrals, and also an introduction to how y can also be something that can be integrated and summed, and how that's eventually going to help us broaden our spectrum of what a function is and can be.
Okay, so to finish up, let's take a look at these two integrals. Notice for GeoGebra, I have to do it with the dx fashion. So I will be integrating these two separate sections just as if I were doing the x integrals. Notice they add up to 9-point continuous 3, which is exactly the 28/3 that we computed doing the integral for the y. Secondly, I've got the area between this line and parabola, and again I had to do it in the x fashion, adding up these two separate sections. So you'll notice that I'm actually getting a 1.8 continuous 3, which is the 11/6 that we calculated.